So we've been discussing chapter 9, which covers approximation techniques in multi-agent reinforcement learning. And we were going to start on the discussion of policy gradient algorithms that start to become a little more complex than the ones that just do like single agent reductions of the problem, where those algorithms, if you're familiar with ordinary reinforcement learning, they look very similar. There are minor changes to handling the multi-agent environment, but otherwise the agents themselves are just attempting to learn as if they are alone in the environment, and everything else happening around them is a part of the environment itself. And one of the environments we were looking at, and like the one that I have implemented and have the most flexibility testing, is this level-based foraging environment. This is like an example of an initial state for one of the environments. Like you can instantiate it. There's different settings for it. You can see, sorry, in this version of the environment, I'm trying to find, oh yeah, so the make environment function, right? We can control like the size of the grid. This is a grid world where the agents can only move in like specific squares. And there's a certain number of agents, and then there are items they have to collect. And then we can control how many items and the level. And this environment can be difficult because for some of the items, like this one, the agents have to coordinate to collect the item, because they have to like sort of pool their level together so they can collect it. Otherwise, any individual agent trying to collect this item will fail. So, it's a good test environment for multi-agent tasks. And you could also set it up as a competitive environment where some of the items could be collected by individual agents. And then, it has the potential to be a very rich environment to study. And the action space for this environment, oh, sorry, this is a single agent reduction of it. But we can see for the action space, this is like just showing there's 3 different agents here, and they each have 6 available actions, just the forward movement directions, and then the collect action and the no op action. So the problem with ordinary reinforcement learning approaches, especially if you try to do what is like a pure centralized reduction of this, where you just try to learn a joint policy over all of the agents, you end up with exponentially growing action spaces. So like here's a single agent reduction of this environment where there's only 3 agents, but we already have 216 size action space. And it's smaller with only 2 agents, maybe more manageable, but we can see if the goal is to scale this up with techniques that can handle a lot of agents, then this is not going to be possible. Although we'll see that a lot of the multi-agent techniques also have a lot of trouble with this scaling. I mean, the action space scaling is not the only problem with adding more agents. Like the task also just becomes more complex inherently. There's way more to keep track of with the state information, because now you have to track the position of just more things in the environment. And that's all important for the state. So, the actual available information is also growing quickly when we do this, which will make it difficult to learn, regardless of the technique we're using. But, we can try stuff still. I did so. There were a variety of techniques that are in this chapter that are tested, and I, prior to like actually implementing all this stuff, which is first like I have to decide what's actually worth implementing. But I wanted to discuss briefly the something useful about testing these algorithms, because I started sort of putting together some of these tests, which in this case, this is for like single agent reinforcement learning. but the concept applies the same to the multi-agent problem. And in single agent RL, we had this grid world environment, which is pretty common. It's basically just a grid that the agent's in. And instead of like trying to collect items and coordinating with other agents, this is a much simpler problem. The agent just has to navigate to a specific, end goal. In this version of it, the goal is always in the same spot. It doesn't change. You could also make a version of this environment where the goal sort of spawn randomly, and then the agent would have to learn how to navigate to an arbitrary location rather than a single location. But this is a stochastic environment where there's an element of the environment that perturbs the position of the agent with some random effect. So it makes it a little harder, but also like the point of this is so that if you're testing algorithms, you want to test like the full range of the algorithm's capabilities. So like an algorithm should work not just in a deterministic environment, but also in a stochastic environment. So I know like this is a trivial problem as well. Like this problem is small enough, trivial problem. And that's important because for testing purposes, like to just make sure that the algorithm that you're developing is correct, it's helpful to have a trivial environment that you already know the solution to. Because then, like there's different ways of testing if the RL algorithm is working, and you can write tests, but really like the only true test of it is to deploy it in an environment where like there is a trivial solution available. It should find, even if the learning rate, the hyperparameters are not tuned perfectly, it should still be something that works. And because there's lots of reasons why these algorithms can fail, especially like the ones we're really concerned about testing here are like the stuff we're looking at in chapter 9, which are gradient algorithms that use approximation functions, learning rates. There's a lot of hyperparameters, and there are lots of reasons with the approximation function. Like there's even a lot of situations where the algorithm doesn't have any theoretical guarantee to find the solution. However, we can create a problem even for those algorithms that does have like guarantees on its ability to converge. And by doing that, we can actually like make sure that there's nothing wrong with how we've implemented everything for the environment, because it should really find the solution. So in here, I was putting together these examples just for regular reinforcement learning, and then I'll extend it to the multi-agent problem. I will just end up using a trivial version of the level-based foraging problem, where it's also a tabular problem like we saw in part 1 of the book, and we can actually compute an exact solution to it. So what this ends up looking like is we make this trivial problem. We see it has 70 states, and we know everything about the environment. And then I made 3 versions of it just because we end up with ordinary RL. We often have different types of problems we want to solve. Like this is a version of the problem with discounting. So like the agent will get a reward for reaching the goal. And then to incentivize it reaching the goal quickly, you need to use a discount rate to discount. But you don't have to set up the problem that way. You can also set it up where, like here, I've set the step reward is -1. And there's no reward for terminating. So now in this case, the reward structure is going to create the incentive, because the agent will try to reach a goal quickly, because the more steps it takes, the more negative the reward becomes. So, and then we can also make a continuing version of the problem. That's also something that has been ignored so far in the multi-agent book. But oftentimes, if you have an episodic problem, like this kind of grid world where you reach a goal, oftentimes it's better to formulate it as a continuing problem where you're just trying to maximize the average reward, because you're basically collecting a goal repeatedly and you want the rate of collection to be high. So you don't actually need to end the episode and then like have this discrete chunk. You can just have it as an ongoing problem. And by doing that with the average reward, I mean, one of the nice properties of it is that you end up with value functions that have more manageable values. Like we'll see here, I'll show the exact solution of this version of the problem. But, this is a great way to incentivize, like, you just want to set a clear goal of, I want to reach the end in as few steps as possible. However, the value function here is going to have large negative values. And that could be a problem for some approximation functions. A lot of the time we want our functions to approximate values that are well behaved, that are within a finite range. So, like I said, this problem is trivial. We can compute the exact solution with a tabular method like I'm doing here, and then that yields this value function, which has the value in every state. We can also derive from this value function the sort of like number of steps it implies. So here, this is a discounted version of the problem with a discount rate of 0.99. So if I take the value at the initial state, which is being done here, and then take the log of that and divide it by the log of the discount rate, that will tell me, what the value function is calculating for the number of steps. So it's about, 19, close to 19 steps. And then we have another, this is a version of the problem where the undiscounted version. And here, the values you could see are these large negative numbers, because now the values are directly calculating the number of steps as opposed to, this function of the discount rate into the future. So here, the values, it's actually a different value here. One of the reasons for this probably is that because this is a stochastic problem, it actually is a different objective. Like picking a discount rate of a specific value in a stochastic problem it doesn't exactly try to minimize the number of steps, because there could be situations where the average number of steps is higher, but the variance could be different in such a way that this objective, it still ends up selecting a different policy. So that's another reason why sometimes you want to use the continuing version of the problem. In this case, if you solve it as a continuing problem, right, you end up with the same exact solution here as if you treat it where you get like -1 reward per step. So this ends up reproducing what most people would want from this problem, which is you want to minimize the number of steps. This version, obviously like this 0.99 is an arbitrary value. Like we hope it just creates the objective we want. But practically, there are plenty of problems where if you set this value at, at 0.9 or 0.8 or something, it is going to yield a different policy. But in this case, it's all very similar, about like 19 steps. So then, now that we have the exact solution, so we know like solving this problem means we basically train an agent that can finish, find the goal in something like 20 steps or 19 steps. And that is very different from, wait, did I show? Oh no, well, I'll show that a little in a second. But yeah, if you just behave randomly in this environment, we could see that, it's like about 3,900 steps is what you expect it to take. So this actually is, even though it's just a simple grid with a goal, like the wind and the stochastic nature, it does actually make it a pretty challenging problem. I mean, this is a very small grid we're talking about, and yet, it's still taking many thousands of steps to solve it randomly. So we can very clearly tell if the thing is working, right? It's either going to take thousands of steps where it's not working at all, or it's going to be, somewhere around, dozens of steps to solve it. Now, I can convert these trivial tabular problems into the type of problem that we would use these complicated approximation techniques on. This ends up just sort of stripping away the state information. So it's not available anymore. And now like the states are just going to be represented by what the state, like the information about the state, like where the agent is on the grid, rather than like you're in this exact state, like 1 of 70, right? In the tabular problem, there was only 70 states. So then, to make this equivalent to the tabular problem or approximation, we can make a state aggregation feature vector. This is a technique where you just group, you just assign states to a group. And normally you just have to make a mapping function. It takes a state, puts it to a group. There's a finite number of groups. So all the states are going to end up, it's just like a hash function, basically. Like we're just hashing the states into buckets. But in this case, I'm just trivially mapping every state into its own bucket. So this does create an approximation function, but it's an approximation function that is equivalent to the tabular solution, where in the tabular solution, right, we have a final value for every state. And because of how I'm constructing the feature vector here, where like here, this is just an example of taking the initial state and mapping it to a feature vector. And here it's showing that it's just mapping it to group 4. Or, I have two versions of this. One is like a special sparse version, which only stores this. You can also do it like, you also should do it this way, because this is how a lot of the state vectors are going to look. They're going to be like dense vectors with real numbers. And this is a good way of testing, because these should yield like the same result, to make sure that all the functions are working properly. So here, right, we have a value of 1 in the 4 index, right? That's the same as what this is representing here. So then by doing this, and now by doing approximation with this feature vector, we can now guarantee that whatever algorithm we throw at it, it should solve this problem. And we can test, like, if something isn't working, it's probably a problem with the algorithm, rather than just, like, doing it this way eliminates all of the other reasons why algorithms fail. Like, usually in approximation, the main problem is that you can't adjust the value of a state individually. Every time you change the value function, you mess with the entire value function, because the parameters affect it globally. But because of this, we get rid of that global interaction. And we're like, if we had a linear function, for example, operating on this, the linear function could change a single value of a state without affecting anything else. And that property is needed to make sure that the algorithm doesn't fail when it's trying to solve this. Like it can fail with, other environments. So, then I just, the remainder of this is just testing the performance of this. This value here is actually the average value per step. So if you invert this, that ends up being the number of steps. And we can see here, like Sarsa, again, this is only running for 10,000 steps, so it's a limited time. It's not going to be perfect. We can see, like, if this is training under these conditions, and we can see, like, even with this trivial problem, there are plenty of training conditions with learning rates and things where this doesn't work, right? This is the problem, also the undiscounted problem. And this has a lot more failure potential, again, because, like, our parameters are going to end up being large numerical values. And depending on the learning rate, it's much easier for these values to diverge than like these values. We could see here that even like this isn't performing as well, but it's still like doing something. Like there's some success. Here we can't even tell what the success is, because, it didn't accomplish the goal even once. So we have this, negative infinite value. And then there's other, versions, but here we could see like this version is much more successful. This is close to the ideal solution, like 24 steps. And then, yeah, this is just a way you could sweep through all the different algorithms you have and make sure that there is some, it's achieving at least some degree of success. This also like 0.03, 0.05 getting up to is like about the ideal solution for this case. So far, these are all linear versions. And then, yeah, also like testing the sparse version and the dense version of the vector, where you have all of the values. And then, yeah, this is all working. And then we have, so this is an example of something that was added for the multi-agent book, and a technique we're going to end up using for multi-agent problems is this synchronous actor critic where we actually have like multiple environments that are running in parallel. This can be a pretty powerful technique, but also a lot of potential for things going wrong and, the actual, you know, the batch learning, just making sure all the gradients are correct and that the data is being aggregated properly. So this is in showing that this synchronous version of the actor critic algorithm is also working. And we can see that like adding more environments seems to help, which is good because we hope that by adding parallel environments, the training is more efficient for this. And also, this version, we have to sort of rely on n-step training here where this is about how far the algorithm's looking forward to calculate rewards in this case, as opposed to like the default would be just 0, where it's just looking one step into the future. But adding values of n, often is helpful for environments. But yeah, this is also a linear training. And then here, let me just go down. So I think so for the nonlinear training, just wanted to show for the undiscounted value function. This is also testing. Those were parameter studies where you just sort of test the algorithms over a big range of hyperparameters and see, what parameters are working. Those are very expensive. Usually when we train, we just want to pick a reasonable hyperparameter and then train and measure the performance. And as we're measuring the performance, tracking it and then deciding if we want to continue to train or not. So this is starting doing one of the value methods and just testing that it's converging to pretty good performance over like a pretty short period of time. Again, this is for linear training. Linear, yeah. And then if we go to nonlinear, we could see, so again, this is the undiscounted version of the problem. And even with this trivial problem, we could see that like the linear algorithms had no problem. If we go to nonlinear training, we can already see that this isn't working that well. Like it's learning something, but it should be doing much better than this. And the reason why this is bad is if you construct a problem like this, notice like the values, right? This is the version of the problem where the value function is representing these large negative numbers. And even for a trivial problem, like the neural network training is going to run into a lot of problems training, trying to represent values like this, which is why it's really important to do some type of normalization on the output. I mean, and better is just to, like, that's why often you see this discounted version of the training, because here you're using discounting. Now, the value the neural network's trying to represent, this is, linear, go to non-linear. Yeah, so here we have a version with a discounted problem in nonlinear training. We could see it's found a better solution even than the linear training, close to the ideal solution. But the value it's representing now is this, it's like 0.04, right? Like this is like trying to learn this discounted value. And because the values it's learning are just in a much more reasonable numerical range, it's going to have way more success. So this worked. And also the continuing, did I do that? I don't know, but this is again an example of the nonlinear training with a discounted version of the problem. And yeah, it just works better. And similarly, the continuing version of the problem would also behave nicely like the discounted version, just because the values are in like a finite range. So are there any questions about this sort of philosophy of how to set up this type of testing and how the state aggregation works for feature vector construction? Because that's really the most important part of this. Well, if
So
not, we
I
can.
was wondering, how does,
Oh yeah.
the grouping of states, compare to, like, when we had the reinforcement learning book where we had, some of the states, grouped into, tile encodings.
Yeah, I mean, tile coding is so tile coding is binary feature representation. In that case, a state will map to more than one feature in the tile grid, so it's a more powerful technique. But um, if you're just doing this tabular reduction, you don't need to worry about like the feature vector representation. All it's doing is mapping each state into its own feature. So there's no need to like the goal of tile coding is to take a state space and actually map it to useful features, like try to map it to useful features where it's not possible to like separate all the states perfectly. Like if you could separate all the states perfectly, it would be a tabular problem. You wouldn't need to do this. Like this is totally unnecessary because you would never solve a problem like this using these techniques. Um, but the point of this is to do the opposite, which is to test the correctness of these techniques on a problem that you would never actually use them for. But it's a useful problem for just verifying that they are working correctly. You know, the gradients are in the right direction and everything like that. But we did, yeah. State aggregation was also one of the things covered in the Sudden and Bartow reinforcement learning. And that's like if you have a one-dimensional state space, like something just has an x position, then you know a common technique for that would be state aggregation, where you just like take the x-axis and you chunk it into pieces of a certain length, and then just whatever the x coordinate is, you put it, you assign it to the group of that chunk of the axis. And you could do a similar thing in 2 dimensions. But then, yeah, the tile coding is useful for higher dimensional spaces where, yeah, you want to store information than just like a single group index. Was that any other question about this? Okay, so the for the foraging problem right now, it's not. It's a little more complicated than the grid world. We did have this also a tabular version of this environment, and like this is now a multi-agent environment. It's not single agent, so there are states, but now there are actions for the multiple agents and a lot more states because now the states also track the position of the agents. So this, even a pretty small problem, still has pretty large state space. It's still totally solvable with normal techniques, but yeah, this would be a good problem to extend all the sort of algorithm testing to the multi-agent problem. And then you can cast this as a non-tabular environment. And that's the kind of thing I would probably do just to be thorough. It especially as I get, if you're like less and less clear about how the algorithm is supposed to work, you really do want to test it on a trivial problem. But yeah, we are going to be talking more about this environment. Oh, is everyone still clear on how this one works, or any does anyone have a question about the level based foraging environment?
Yeah, well, it makes sense, since, the items are just, noted in, a particular level where it has to have, coordination between agents in order to pick up some of the items because a singular agent is not able to singularly resolve some of those items.
Yeah, and I so in testing this level-based foraging. I made another thing you want to do in testing is like have the ability to make different sort of difficulty versions of the problem. So that's another thing I was looking at and wanted to do a little more thorough job of. The book does discuss this briefly here. They show the success of this independent actor critic algorithm on a version of with 2 agents and 2 items, and they're using a 15 by 15 grid. Later on, they have smaller versions of the grid for other algorithms, and then this is, of course, like even to get this level of success, they say this did take quite a bit of work. I mean, you're talking about like, 3 hours of computer time. So if you're trying to like quickly iterate and see how things are working, this is a while to wait. And similar, like with this is sort of, this is working somewhat. We could see that this algorithm is having a tough time scaling. Like this is a much more difficult problem. We could certainly make the problem easier than this one, and that would probably be useful for testing algorithms. But it does bring up the question of really like how hard is this problem, and how does that difficulty scale with different conditions. So I made like some test versions of it here, um, which I'll add to over time. But the like an even more trivial version of this is where we just have 1 agent, right? So this version of the problem does not require any coordination, which is a big part. Both, this makes the action space much smaller, and it eliminates the complication of figuring out how the agents coordinate with each other. So now this is just a single agent collecting some items, all of which it can collect. So this will be the easiest of the environments. And then we can make the 2 agent, 2 item version, but in a smaller grid. And then we can make, progressively larger grids. And then like the hardest version they have, and there is 3 agent, 3 items in the large grid. So this is what it sort of looks like with this is a smaller version of the problem I was working with, where now it's like a much smaller grid than 15 by 15. It's only 5 by 5. So this sort of eliminates the size of the grid you have to track, but it still contains all the complexity of the agents needing to coordinate together. I think for really testing that the solution is working and it's doing what we want multi-agent solutions to do, which is figure out the coordination between agents. This is more purely focusing on that, whereas there's a lot of difficulty with a large grid like this of just tracking where you are in the grid. I mean, you could even make, like this is just the agents are not very far away. But we can test the performance of this with random behavior to see like, how hard is this task really if we make the grid small like this. So I was testing a little bit of that here. Okay, sorry. So this is I wrote this, so it's printing differently than the other things. But this is the task 0 I made where there's only 1 agent. So this has no coordination on the small grid. And we can see that the mean value is 133, 134. So that's how many steps it took for the agent just randomly selecting actions to collect both items. So now, this task 1, it's the same exact grid size. But now there's 2 agents and 2 actions. And also, because I wanted the statistics to better represent the difficulty of the problem, when I made all of these tasks, except this one, but I'll fix that later, all of these tasks have this force cooperation tag on. So that means that all of the items that spawn, they can only be collected by both agents working together. Because if a task is finished more quickly that I randomly create, it's possible that one of the reasons the task finishes quickly is because one of the items is just easy to collect. And for testing, for consistency, I wanted the coordination challenge to be there for every item. So just adding the second agent and the need to coordinate takes the mean value up to 6,700 steps from like 130. So we could see the exact like scaling of how difficult this is getting, just adding the coordination, and also by making the grid larger. So this is now the same task as this, but in an 8x8 grid. And now it's like 33,000 steps.
So, currently, to note about, the coordination that's only, currently being encoded through the optimization function currently, and not through, allowing like agents to actually communicate with each other.
Well, this is also just random, right? Like this is showing the time to success if the agents just behave randomly as a gauge of how hard it is. But yeah, like this, so there's no like training here for that has improved their behavior. But yeah, the algorithms we're gonna look at, um, like the agents will attempt to learn their behavior themselves, and they also have information about the other agents, like their position, sometimes, and their maybe in some later ones the actions they took. But yeah, there's no communication between the agents for the algorithms we're currently looking at. But is that what you were asking?
Yeah, but I guess, that answers the question, since, the statement of how those agents are currently just, traversing randomly and by random chance, currently it just shows that the mean amount of steps is grown significantly very fast.
Yeah, the thing I'm trying to figure out here is just sort of the scaling difficulty of this problem. So this is now in a 15 by 15 grid. The problem is these aren't even accurate statistics anymore because I had to. I'm capping the max steps, so the mean value is being reduced by this. The median is probably still representative, which is it looks like it's what 10 times larger than this one. So yeah, and then for this task now the median is like, wait, this is for, I'm not sure why this value is lower. It's probably just because I have fewer samples here. But yeah, this should be the hardest version of the task. I also made a plot here of the scaling with the size of the grid. So we can see like as the grid gets bigger, this is still two agents, two items, they have to coordinate. And it does appear to be scaling like exponentially here with the, how often we'd expect random agents to succeed in this problem. And up here, even with just a 10 by 10 grid, right? This is way smaller than the 15 by 15 in the book. Right, we can already see this is like a really large value. Yeah, 8 by 8. So this jumps up to 15 by 15. We could see, yeah, this is like 33,000, and now we're up to like 76,000. So like the problem with this is that like you may not have any information to go on to do learning until you reach this threshold. So you do end up needing to train for a lot of initial steps just to sort of get a foothold on the problem before you can have success, training beyond that. So this, like, one of the reasons why we do these algorithms in the book where we're learning like independent policies for each agent. So here's a case where like we have for the n agents a separate policy function where the agents are just learning the policy for their own actions. And whatever is relevant about the other agent's actions updates their policy in the training process, but they're not using it. Like there's no coordination happening, but it does make the individual functions a lot more tractable. Whereas if you try to solve this problem, like I mentioned before, by doing like a central learning reduction, what you end up needing to do is cast the problem as a central problem where you define a new reward objective. Like here, I'm defining it as a cooperative task where the agents are trying to work together to collect the reward. And then we have, this, I'm just sticking for now with the two agents, but we already have this large, size 36 action space. And, this has bad scaling properties. It may be hard to learn a solution here. But I was trying to see, depending on, like, if I make the problem easier and easier, is there a point where you can do central learning and perhaps it gives some insight into the hyperparameter space? Because, there's a lot of reasons why this could be going wrong. I did. Wait, so anyway, this is a value function method trying to solve this as a central learning problem. We can see, so what did I say was so this really didn't work. And actually in the book, even when they cover independent learning, they don't even deal with the value function methods, even for this version. Independent learning should scale better than the central learning. And they just skip straight to the actor-critic method, which there are a lot of reasons why the actor-critic method is better for approximation, especially when you have simple approximation functions like a linear function. I mean, here they're like the book is also talking about, like, for these graphs, a neural net architecture with 64 by 64 hidden layers. And here, this is just doing linear approximation with the feature vector we sort of discussed last time, but all I'm doing with the feature vector, which I think I have a description of it here, but yeah, like to form the feature vector, I'm just sort of taking the state information about the positions and levels of the agents and items, and there's a version of it where I map it to like binary information and just concatenate it together. There's a version where I store the actual numerical values in a smaller vector. But the sparse feature vector is going to work better probably for both types of approximation, but especially the linear approximation, because one of the benefits of it, if you make a sparse vector, like here for this size of the problem, you just get more parameters to work with for the linear function, right? Because it's stuck with using one of its dimensions is tied to the length of the feature vector. So you end up getting more parameters to work with. And you're just representing the information in a more pure form. So it's probably better for the nonlinear approximation as well. So we can see for policy gradient. Oh yeah. So here is an example for the smaller problem, right? Only a 5x5 grid, but still, takes thousands of steps to solve with random behavior. And this is an example of training it as a central learning reduction. So this is like the policy function that it's learning. And you can see, because this is central learning reduction, right? This is a 52 by 36 matrix where the 36 is the dimension of the joint action space. And this training with just a linear function, right, which is way less complicated than the neural net architecture, did actually manage to solve this, or at least do way better than random performance. You can see these are the performance statistics of this linear policy function in the environment. So the average is like 47 steps. The max is 245, and out of all the samples collected. And we can see Oh, this is still running something, but when that finishes, I can show how this is working. But this is an example of one of the episodes that completed in 24. Or wait, no, how many? Yeah, I believe this completed in 24 steps. And what you're seeing here is the policy function, or because it's a central learning reduction now, this is a joint policy function over the 36 joint actions. We can see here that because it's policy gradient, these are stochastic policies, and it's a linear function, so it's highly restricted. It's far from optimal. Like we could see here, obviously, the double collect action should not occur here because the agents are not in position to collect. But then the next favored action is double left, which would then bring these closer to a position where they could collect. And the reason why this is taking 24 steps or however 47 on average is because there's a lot of policy situations where like this is not a close to a deterministic policy. Like there's a lot of probability in the top 3 actions, and you end up with a somewhat inefficient solution. But a lot of that is like this may be the limit of how good the linear function can even do in this problem. I'm not, it's hard to know that. You'd have to keep training it and see. But by doing this, you can start making the problem more difficult, and you can see where the linear function, like if it even has some amount of success in a much more complicated, like a larger grid. And probably, you would just do a larger grid at this point and see if it still has success. But this at least shows that, like at this scale of the problem, central learning can still work with this feature representation. And then, the value, if you try to do independent learning, like at least the value function methods I had tried on this did not work very well. That's like stuff like independent DQN, which is mentioned in the book up here. But again, not used for any of these graphs. So it's not used in the graph. I'm guessing it's because it did not work very well compared to the actor-critic methods. But what the DQN is learning, right, these value functions, we look at like the linear function. So now, right, we have 2 value functions, one for each agent, and the number of parameters is much smaller because now we're just learning over these 6 actions, right, as opposed to the 36 joint actions. So in theory, this can scale much better. But again, basically for the case of value function learning for this problem, we have just kind of 2 failure cases, so it's hard to tell if one method is scaling better. Whereas, yeah, I'd have to try the multi-agent version of Actor Critic to see how that compares to the central learning reduction version, where you learn, yeah. But again, with the central learning, you have the scaling problem across the joint action space, which does also come up in some of the stuff in 9.4, because one of the things this gets to in the middle of the section is learning joint action values for the agents. And that also has a similar scaling problem where you have to sort of have a function that represents values that you end up calculating across the joint action space, which is, scaling exponentially with the number of agents. Unfortunately, you end up, if you're trying to get away from the complications that you get from central learning reductions, but you sort of reintroduce it with some of the joint action learning. So let's see, and this is still running something with nonlinear. Oh, okay. So this was also running, the same task, but with the same network architecture they mentioned in the book, which is 64 hidden layers on the problem that I showed with the linear solution that worked. So this is training, again, figuring out the right hyperparameters for this It's pretty difficult. This is actually still running, as we can see. But at least so far, it looks like the performance is now like 0.06. And what the linear? Yeah, so this was the linear solution. So this was like 0.02. So I guess even though this hasn't completed yet, I can already see that the neural net version of this is also working and probably approaching much closer to what the ideal solution is. Because right, one over, I mean, what is one? Like the average number of this performance is basically like the average reward per step. So, right, this is like 16 steps. It should correspond to about solving this in 16 to 17 steps. So that is what we would expect, right? This neural network should be more powerful. But again, the amount of training time, I mean, it's slower to train and may need a lot more training steps to actually work. Oh, and actually this, oh, okay. Yeah, this I'm actually training with synchronous actor critic as well. So this is like the central learning version of what they do in the book here for with the independent actor critic. So this could be directly compared between the two methods to see how successful it is. Where like the claim in the book is that this method should scale better. Because each individual agent has to learn over a much smaller action space. But yeah, okay. So this, I'm glad this does appear to be working. We could see this did not, it hadn't been working that well with a non-synchronous technique. I mean, this again, like makes better use of scale. I mean, I'm only using 8 environments here, which isn't that much scale. But this just controls how big the batch size is for training. So, you could bump this up to a much larger batch size, but you also might wind up with other problems. Like the learning can become more inefficient if the batch size is too high also. So, it's another hyperparameter you have to tune. So like for actor critic methods, like the only difference with the central learning reduction, where in the central learning reduction, I'm just taking the problem, I'm making it equivalent to a single agent problem. With the independent version, you just have n of these single agent problems. And you have to manage, like collect the reward, which is across all the agents in the environment. But then once you collect it, you just send like all these functions here, the advantage calculation, the gradient, right? This is computing the exact same thing as if each individual agent was learning with its own actor critic algorithm. And all the value functions also are just for, right, this H represents what information is available to the agent. And so each agent has its own its own critic and actor functions, which are conditioned on what that agent can see. Now, I believe this graph in the book, and also the way that I ran this when I was doing the independent learning, is that each agent is just seeing the state information of the problem. Like this H here that's being used, even like for this graph, is just like the full state information of the problem. So the agent's observations are the full state and just the current state, right? Not the history. Like this means the history of observations, which includes whatever the agent could have seen going back to the start of the episode. It's very difficult to make approximation functions that handle, right, arbitrary history lengths, which is why often, especially when we're testing things, it's easier to just, use the state or have a finite history, like maybe the last 5 steps that we put into something. The only difference between this algorithm and the next thing which is introduced, which is centralized critics, everything is exactly the same. Every agent has its own distinct actor and critic, but there's an additional input we make available to the critic function only, which is Z. And all Z is a representation of what is other information that's not available to the agent at its time of deployment, but we do have access to during the training time, which could be like the full state information of the problem. So this is used to train the critic. When the agent's actually deployed, we don't even use the critic function, right? This is only used in the training process here, right? It's only used to calculate the advantage function, right? Or just it's just this difference between the expected the observed value here and this expected value from the value function. And then this is used in updating the actor function. But this pi, like the actor function is all that's needed for deploying the agent. So nothing else like the central critic, like notice even though this is centralized actor critic, like there is no central critic. There are n distinct critics, but when they're trained, there is some centralized information represented by these z's that is used for training the critic value function. That's the only difference. But in the case of this example and the data I showed, I'm already using the state information for both the actor and the critic function. So there is no distinction between centralized actor critic and this version of it if H is just the same as Z. Like you're just giving all the available information to all the agents. I mean, there is this other issue that actually the current state of the environment is less information in theory than what the agents might need, because if you include the history function, this history might include the past behavior of the other agents. And because you may have an algorithm that tries to estimate how the other agents are behaving, which is not contained in the state information. So if there's a task that involves complicated coordination or competition between agents, part of what the agents are optimizing is responding to what they think how the other agents are behaving. So even though often when by giving the state information as the input, that's seen as like more information than would ever be needed, it is technically less information than what should be available in this whole observation history. But this problem probably doesn't require that sort of history information because the agent should be able to figure out how to coordinate. There's some optimal way to coordinate that doesn't depend on, knowing at the current time in the training how the other agent is behaving. Because what we hope is that all the agents just converge to the optimal behavior together, and there's a solution that can be derived without like any sort of communication or estimation between the agents. But I don't know if Dimitri, if your question was related to this thing or how the inputs work for the centralized critic, but did my explanation make that clear? Okay. Maybe Dimitri's not there anymore. But if anyone else has a question about, how this works, feel free to ask. But yeah, the only difference is this. Oh, sorry, Dimitri. Yeah, did you have?
No, I guess that diagram clarifies that a bit between the history, but well, at least how they're basically inputs.
Yeah, I mean this HI technically is the current observation history available to agent I. at a particular time. Well, here it's at or time t. So this is like the history available at time t for agent I. But yeah, this H just represents the observables to the agent. This is like the information that would be available in theory when the agent is functioning, like in the environment. And this is information that the algorithm might know during training, but isn't necessarily available to the agent when it's deployed. But I already mentioned that the way we're training these agents and deploying them, they're going to have, for this level-based foraging example, the agents are going to have the full state information anyway. So for this particular problem, it's a distinction that does not exist between these two algorithms. But the distinction is just whether this Z is present or not. Where Z is just whatever centralized information you want to, make use of during training. There is a whole discussion in this section about what kind of information should be used for Z, what should be included. And there is like a theoretical idea that like you shouldn't include this extra information because it increases variance during training, but then the authors say like the conditions where that happens is not, it's only in like a very narrow type of problem, and practically it does help to include additional information. So I don't know, there's not really a clear answer. They don't, I mean, here they do show an example graph. Again, there's no implementation details of what they're doing with this. This is another environment game where you have two agents. This agent is trying to, like, needs to select one of these objects, but the object it needs to select, it doesn't know. This agent knows what object it's supposed to select and has to communicate that to the other agent. So this agent can share some bits of information, and it has to learn how to like encode these shapes with bits of information, and then this agent has to learn how to interpret that and collect it. So we could see for this, they're claiming, I mean, the centralized version of the problem seems to do a little bit better. It's probably still within the variance limit of this, where we're not sure how much of a difference it's making. But the example they use about why the centralized critic might do better in this environment is because, like, there is a clear separation of information between the speaker and the listener agent. So if during training, the critic can actually see the information that the speaker has, the critic for the listener. So that might help in the training process. Whereas the listener, its policy function itself is not going to have access to the information from the speaker. So anytime you have a partially observable environment, there may be some benefit to having, using centralized critics. And also, here they're also including the state history as well in the central information, right? So not just the current state, but the history of states. Again, they're starting to add a lot of information to what's available. But yeah, for a game like this, this would be important to track, like, for the critic to track, okay, like in this environment state where I had to collect this, that's how, this is an example of how the speaker was trying to communicate this information over, some number of time steps. So for the normal actor-critic algorithm, right, the actual critic function is a value function, a state value function. So it just contains a single value that is sufficient to calculate this advantage value, which we need because we just wait for the next transition to happen. So we know what state the agent will end up in, and then we use that state to then compute the value function at the next state and use that for the advantage. Another thing you could do, which is not really useful at all in ordinary reinforcement learning, is to compute a critic that uses an action value function as opposed to just a value function. So now the critic, right, would be this Q function where Q is now, I mean, this technically, these are values across the joint actions, but in order to use this, we would have to wait for the next state transition, also wait for all the action selections to happen in the next state. This is exactly what you do in the SARSA algorithm, which is mentioned here. Right? So it's state action reward state action. So you can only use SARSA or regular RL by waiting for the actions to be selected at the next state, and then you're training this Q function, and you have to wait for the action because, right, like the Q function doesn't have an output value until you give it the actions that you care about, because it has a different value for all the actions. In this case, this is a Q function, the way it's written here, over the joint action values, which actually means that learning this function is the same as the type of function we have to learn in what I was showing earlier with the central agent reductions. If you do a central agent reduction, you have to learn the policy and value functions over the joint action space. And that's the same thing happening here. And otherwise, the critic algorithm, like the actor critic algorithm, is then the same. It's just that instead of using the V function at the next state, you're using this Q function, but at the next state and the joint actions that were selected. And if you just do that, there's not really any point to this, right? Because you're just ending up with the same thing with a harder function to learn with the actor critic algorithm. There's also a point here how, again, because of that curse of dimensionality that you have with a function, they say one way you can handle it, don't learn a function that outputs a value over the joint action space. Instead, output action values for the agent, the current agent, so just its action values, but then use the other agent's actions as an input to the function. So then instead of one function outputting, 36 action values like we'd have in this problem, you would have the function output 6 action values, but we would then put in to the input the actions that were selected by the other agents to get. Otherwise, we'd throw out a bunch of information if we outputted all 36 joint actions because not all of them happen. So we do need to know. I mean, this is also wasting information because we only actually need to use the action value that was taken by our agent. But, this is like a nice tip of a way to not, an alternative. If you did need to calculate all the action values, though, for this, all the joint action values, this is way worse because now you have to run the function forward a bunch of times and replace the input here. I mean, you could do it as a batch, but it's still going to be more efficient if you just had a function that output all of the joint action values in one go. So anyway, like doing this, there's no reason to do this, right? If we're just going to do the regular actor critic algorithm. So there is, however, a point to this in the multi-agent context. And that they start introducing here with this idea of counterfactual action value estimation. And the idea here is that we consider values or rewards that we could expect to have if we had taken a different action, right? But the other agents had taken the same action. And this is the kind of thing you can only calculate by either having, like here, they're showing the actual reward function for the environment, which normally we don't have. All we have is we can sample from this. Or you need some estimate of the joint action values to do that. Because otherwise, when we just do independent learning, the actual transition of the environment and the actions of the other agents are all mixed together in the output. So we can't analyze these like counterfactual type things. Now, of course, our function also has to be meaningful. Like if this function hasn't converged to anything, these counterfactuals are all going to be, they're not going to be useful information. But they get to later, so this is a way of, so difference rewards. I mean, this is just a way of reducing variance, I believe, in the training, where the goal here is to, instead of like using the reward that our agent got, is to then just, we're basically just normalizing that reward with something like a default action here. Like there is no real good way to pick the default action. The better method here is to just, this is sort of like what we do in expected SARSA also, same idea, where we take the current policy of the agent, and even though it did in fact pick this one action, like A sub I, we can still calculate like hypothetically what is the reward across its policy selection. So not just like for the one action, this is just a common technique to use expected values rather than sampled values as a way to reduce variance in training. But really that's all this is doing, is just reducing variance, right? This part here, again, it's just changing the advantage function so that there's this baseline value. This is also what we do with reinforce with baseline. This is just a way of computing a baseline value that makes use of the joint action value function. Now notice to do this, we have to write sum over, yeah, our agent's actions, right? Which hopefully we all get as a single output from the action values of the other agents. So the reason why like they're suggesting this architecture here is because the way we're going to use this is we're going to have access to the actions of the other agents as an input. And then we just want to use these values as a way to compute an expected value to reduce the variance here of the advantage function, right? So yeah, it doesn't change. But then the baseline suffers from high variance. So I mean, probably like they mention a bunch of caveats at the end here. So far, doing this doesn't seem to have much of a point, right? Because like in theory, we have a baseline which can help improve the advantage calculation, but then practically this itself is high variance, plus we have to learn all these action values. So far there's not much point to doing this. Now, typically when we had these estimates of the joint action values for tabular problems, the point of that was to look at these sort of game matrices where, right, this is the game matrix where it shows the joint rewards for a single game. It's not a stochastic game. And in the past, when we had tabular game problems, we were trying to learn what this matrix looked like for the different states that we end up in. Because then we can use this matrix to calculate equilibrium solutions and, you know, learn like Nash equilibria behavior, which is necessary for certain games where independent learning is not sufficient. Like when you do independent learning, you're just hoping that the agent optimizing its own behavior is enough to learn how to solve the problem. And for common reward games, like what we showed, like the level-based foraging game where it's cooperative, it's probably fine, and you don't have to worry about these sort of equilibrium calculations. But if we end up like, this is one of the games like the stag hunt game, we had discussed in part 1 of the book all these different matrix problems and their different Nash equilibria. The problem with these types of games is that they can have more than one equilibrium, which is mentioned here. Like the StatCon game, it has two different Nash equilibria, and one provides a better outcome for both players. The problem is if you try to train agents to learn this, they're more likely to learn the worse equilibria, the worse equilibrium, because there's a note here in the book about during the training process itself, this is a less risky equilibrium to attempt to learn. And it's because of how the reward structure is. Like, how much are you likely to give up if your opponent doesn't cooperate with you in the correct equilibrium? You end up with sort of basically more to lose here than you do here. So the joint action values are, it's what these equations are showing here. But again, like this is probably not relevant for the level-based foraging game we've been looking at. But the policy function now ends up, I mean, the actual agent is still going to follow its policy function. But for the purpose of computing now the loss function, which makes use of the advantage calculation, the advantage calculation now, instead of just using the value function like we had before, is now using this hypothetical policy of the other agents that actually is computing some sort of equilibrium based on the joint action values, right? So here, the U, this is like, these are the true reward values of the game if we actually knew what the values were, like here. But instead, we're replacing that like with this Q function, which is computing things over the joint action values. But now, to do this calculation, this argmax, we actually need now to go through all of the joint action values to compute this. And this has exactly the same scaling problem as the central agent reduction. And it's even worse because in the central agent reduction, we construct a function that would output all of the action values. Here, we've separated now the input and the output, the joint actions. So this is going to be really awful to iterate through, updating the input each time and getting just one slice of the action values. And they make a note of it here. I mean, I guess there's no note here about how long this took to run for these problems. But this is like a niche solution. Like there are situations here, they actually create a version of level-based foraging where this is important, where there's a penalty function. So normally, if an agent tries to collect an item on its own that it can't, nothing happens. This version of the game, there's a penalty if it tries to do that. So the point is there's an equilibrium solution in this game that is likely to occur where the agents just never collect an item, right? Because that at least avoids the penalty.
So basically, the optimization function is getting augmented in order to force the better equilibrium, essentially.
Yeah, what we call like a Pareto optimal equilibrium. I mean, we also talked about, yeah, it's a way to distinguish between multiple Nash equilibria, like in this simplified version, these two, where they're both equilibria. The problem is if they're equilibria, that means that it could converge to it. And then if there's one we prefer, like the higher value outcome, this is Pareto optimal, whereas this is not.
And so, in the optimization function where, the first term where it was, subtracting the value function, where the second term was, so in 920, so the Q policy of HIZT of action of the agent and the action of the other agents basically does that.
Yeah, and this like pi plus here, right? So the important part is we're taking the expected value assuming the other agents are following this hypothetical joint policy that involves actually optimizing this Pareto, having this Pareto optimal, equilibria.
But then, since each of the agents, have their own policy, how do you actually compute, the hypothetical metric of a
Well, it's
unified
just,
policy?
I mean, so it's using, right, like this is taking an argmax over Q, where Q is these, what that particular agent has learned so far about the joint, you know, action values of the other age, right? Because like this Q, actually, wait, in this case, it's only learning its own um action. Oh no, yeah, so yeah. So it's still fine. So yeah, this is the reward from the perspective of this one agent, I believe.
So it's just stating, one of the policy, the Q value of the policy of one of the agents that, is the most learned one essentially.
Yeah, I mean it's yeah calculating its own Pareto optimal action. Yeah, because like looking like this Q function is allowing it to test all the joint action values of the other agent's actions, but it's only optimizing its own um action selection here, right? I mean, actually, what it's saying here, it's a set of policies to maximize the return of agent I, even though it's the policies the other agents are following. So it's considering hypothetical policies of the other agents, but trying to maximize its own performance. Right. This probably, if you look back at the part one of the book where they talked about Pareto optimal distinction of two different Nash equilibria, it's the same thing. It's just that there we actually had this U matrix probably, whereas now, right, we're using this approximation function, which is not just averaging values, but it's also like a neural network that has other issues with mixing action values, but it's all we have available in this case. Yeah,
All
so there's
right.
a reference here
Yeah,
to
that,
equation 4.16, which is the chapter on Nash equilibria. Oh, wait, I didn't mean to
yeah.
go back to that. Okay, here. Yeah, this is just the equation for Nash equilibria.
All
And
right.
here's
I
the
guess, that makes sense. And, using sense of the extra, computation that was used to, have the actions of the other agents being used in order to accumulate basically a vector of Q actions of that particular agent and other agents,
yeah,
agents
because it's like
presented as a
assuming
hypothetical.
yeah, it has to consider because also like during training, the other agents have some randomness in their action selection. So, but for the policy update, we want to update it using what we believe is like the Pareto optimal policy based on the current value, like action value estimates. But to actually calculate the Pareto optimality, we need to know like this true U function, yeah, across the joint policy space. But yeah, I mean, part of the criteria for something being Pareto optimal is that it's good in some sense for all of the agents involved, and also like it has to be a no conflict situation for it to be applied in a useful way, which is true of what we were looking at. right? So this has like a very limited use case. Uh, yeah, like it has to be, and also like you don't know ahead of time if a game is no conflict. Like you can maybe figure it out from the structure of the rewards, but here they, I mean, like we know the level-based foraging game is, they're trying to coordinate, collect the items, fine. Like we can construct it as a no conflict game. But yeah, like this technique only applies to a situation where there's a common goal. I mean, even like when you have these games, right? You don't know ahead of time with one of these matrix games what type of a game it is. Like it depends on these numbers. And yeah, like we now that we know the properties of this game, we know it's like a game with two Nash equilibria, and they're both like good outcomes for both parties. And there's one outcome that clearly is better for both. But when you do a multi-agent learning problem, right, like you're like learning what these values are in the different states through the training process. You don't know ahead of time. If you have any kind of problem that's non-trivial, you're not going to know this ahead of time. Meaning you wouldn't know if this is appropriate to try to do. But again, like in order to do this and compute this, you have to take this argmax over a I minus, which is this input. And this is not going to scale well. I don't know how long this took to run, but at this point, like you may be better off just doing central learning. Because with central learning, you can define, like here, the way I'm doing it, right? I reduce the level based foraging to a central learning problem. And I took the sum of the rewards. So like I'm already defining like the objective of like this objective is better. I guess I would have to try it with the penalty case to see. To see if it gets stuck in that equilibrium. But I'm guessing it wouldn't get stuck because we're not doing independence learning. So you still have the benefit of the guarantees of like single agent reinforcement learning and the properties of like finding the optimal policy. Like you shouldn't get stuck in a local optimum as part of the problem construction itself. It could happen because of the like a nonlinear approximator, but it shouldn't happen as a result of the problem itself. And that can happen here with independent learning where the agents can get stuck, right? Because the agents in independent learning, the agents can get stuck in an equilibrium, like a Nash equilibrium, because if they deviate from that behavior, they're going to get a worse outcome. When we do central learning, because we're operating on the joint action space directly, I don't think you would have the same problem because there's like local optimum in all kinds of single agent RL problems, but the policy gradient theorem still should guarantee that you improve the policy anyway. And yeah, because like once we recast the problem as a central learning problem, we get rid of all this like equilibrium selection issues. Because the reward sum here is still going to be 0, and if we do this behavior, the reward sum is higher. So I would guess it would still find that, and that would be a way to circumvent having to do this. I think it would work better, but I don't know. I'd have to test it. It's probably worth testing though. Uh, Decentralized actors, blah blah blah. I mean, also you may have to do this if the actors themselves can't like rely on a centralized critic, or sorry, a centralized controller that tells them what to do. It's another reason why you may have to do this. But I'm guessing this has pretty limited use cases just because of how inefficient it is to calculate this argmax, and the problem that you don't know ahead of time, right? If the problem is actually like suitable for Pareto optimal equilibrium calculation. But yeah, so at least like so far, there's not. I would say that there's a pretty limited use case for this replacing the normal critic with an action value critic. And I think in the next sections, we're going to get to algorithms that actually have some more practical uses. Because I believe the rest of these are actually implemented in their pseudocode, like value decomposition networks, Q mix, etc. So I guess, yeah, next time we'll try to move on to value decomposition, see what that looks like, and try to have more of these testing environments ready so that way we can compare like central learning reduction to these techniques and see how much of an advantage it has. Yeah. Are there any other questions about this or suggestions for next time, or does that plan sound good? Okay. If there's no questions, I'll just thank everyone for coming and yeah, hopefully see you next time.